So good morning everyone. So today we shall discuss some the basic concepts of the valence bond theory. How the valence bond theory is very much useful for predicting the geometry of a particular complex, or for predicting the magnetic property of a particular complex. So all these things today, the merits and demerits of valence bond theory, and then the postulates of valence bond theory, all these things today we shall discuss that one in detail. So first we'll move on to the introduction part of the valence bond theory. This theory was developed by Lennon Smalling. So it is otherwise called as the Pauling's theory. Maybe theory is otherwise called as the Pauling's theory. This valence bond theory mainly talks about the overlapping of the atomic or the hybrid orbitals of individual atoms. Next comes the postulates of valence bond theory. Lennon Smalling, he has framed some rules and regulations while naming the or while studying the predicting the geometry of a particular complex. How a complex is formed? A complex is formed by the overlapping of the vacant metal orbitals and the ligand filled ligand orbitals. So all these things has been discussed by the Lennon Smalling under the postulates, under his postulates. So the first postulate is given here, that is, the central metal ion, it makes an available number of vacant orbitals which should be equal to its coordination number. So these vacant metal orbitals, it should form the covalent bonds with the filled ligand orbitals. Then the third postulate is the covalent bond that is formed, which is formed due to the overlapping of the vacant metal orbital and the filled ligand orbitals. So there is a metal ligand bond is formed due to the overlapping of the vacant metal orbitals and the filled ligand orbitals. So this complete overlapping of the vacant metal orbitals and the filled ligand orbitals leads to the formation of a metal ligand sigma bond. Next comes the concept called hybridization. A very strong covalent bond is formed only when the orbitals overlap to the maximum extent. This maximum overlapping, it is possible only when the metal vacant orbitals undergoes a process called hybridization. So here we find different types of overlapping. I have listed out some of the types of overlapping here. That is SS overlapping, SP overlapping, and then PP overlapping. First we'll see about the SS overlapping. See, in this type SS overlapping, one S orbital overlapping with the another S orbital gives you the SS orbital. Here the familiar example we have given here is how the hydrogen molecule is formed from the two S orbitals. So this is called as SS overlapping. Next comes the SP overlapping. Here the one S orbital overlapping with the another P orbital gives you the SP overlapping. Here also the sigma bond is formed, here also the sigma bond is formed. Next comes the PP. So here the familiar example we give for SP overlapping is the formation of HCl or the formation of hydrogen chloride. So all these things can be given as an example for SP overlapping. Next comes the PP overlapping. How a sigma bond is formed from the PP overlapping. So this is the formation of sigma bond in the PP overlapping. There is one P orbital overlapping with the another P orbital gives you the sigma bond. So this is the sigma bond formed here. So this is how the sigma bond is formed. Next comes pp overlapping can also lead to the formation of a pi bond. See here the orbitals overlapping, it overlapping upwards to the perpendicular axis. Okay, this is called as a linear overlapping of the p orbitals. So linear overlapping of the p orbital leads to the formation of pi sigma bond. In the case of the formation of pi bond, here also both the p orbitals are involved. Whereas here, see the overlapping, how it occurs. The lateral overlapping. Here, this is called as a lateral overlapping, or it is otherwise called as a sidewise overlapping. So this is how pi bond is formed due to the lateral overlapping of the pp orbitals. So one orbital, one is above the plane, above the nuclear axis, other one is below the plane. So this is how sigma bonds are formed. So according to the valence bond theory, if a complex have the coordination number 2, the predicted geometry is linear geometry, and the hybridization involved in that particular complex will be sp hybridization. And then whenever there is a sp3 hybridization, the predicted geometry will be a tetrahedral geometry, and then the coordination number, based on the coordination number 4. So if the complex having the coordination number 4, there are two possibilities. One is one may undergo sp3 hybridization. Another possibility is the hybridization. Here it involves dsp2 hybridization. The predicted geometry is square planar. So the square planar complex will have the dsp2 hybridization, whereas the tetrahedral complex will undergo the sp3 hybridization. But both are having the same coordination number. Here also we find that if the coordination number is 6 for a particular complex, for the octahedral complex, the types of hybridization is D2 sp3. Then the same octahedral complex, the sp3 D2 hybridization may also occur. Next comes the prediction of the magnetic properties of that particular complex. A species having at least one unpaired electron is said to be paramagnetic. If the complex doesn't contain any electrons, unpaired electrons, that particular complex is said to be a diamagnetic complex. So this is one of the merits of valence bond theory. How we are able to predict whether a complex is a paramagnetic complex or a diamagnetic complex. So the valence bond theory is very much useful in predicting the magnetic moment of a particular complex. Next comes the merits of valence bond theory. So this theory provides a pictorial representation of a complex. That is, it's a satisfactory pictorial representation of a complex is given by the valence bond theory. And it also a very good model for the qualitative prediction of the magnetic behavior and the reactivity of the complexes. Then comes the limitations of valence bond theory. See, some complexes may be colored complexes, some complexes may be colorless. So the reason for the coloration of this particular complex is not clearly explained by this valence bond theory. And then another drawback is that it cannot explain the reaction rate of the reaction and the mechanism of the reactions. And the third drawback is it doesn't offer any explanation to the absorption spectra of the complexes or the reactivities. So hope you have followed the basic concepts of valence bond theory and the merits of valence bond theory and the demerits of valence bond theory. So thank you for listening. Thank you very much.